particularly in with black background and white things, and that's also the environment. I'm going to show you some demo code as well. So that might be a little bit difficult to see if you're sitting in the back, so you might want to move forward. I've tried to increase the scaling of my screen as much as possible. So, but now you have been warned. We have room here in the front. All right, so. I just gave another talk, and I just need to reset my brain a little bit to see what is this one about. All right, got it. All right, so back in the 2014-2015 timeframe, I was asked by one of my recurring clients to come back and help them out as a freelance software developer. I'd done some work for them before, and then I went on to do other things, and then I came back because they wanted my help with some stuff as well. And they've been pretty busy while I was gone. And this team was a team of very skilled developers. So they had lots of great things that they did. And one of the things that they did while I was gone was that they'd enabled continuous delivery. So I learned a lot about continuous delivery from these people. So that's sort of like the organization they were. They were really good at what they were doing. But this talk is not about continuous delivery. It's about another interesting thing that they did, because also while I've been gone, they've implemented a logging system in their production system. So whenever the production code was running, it would log to. I think they used this elk stack, as far as I remember. So we started, I started helping them, creating new features and so on. And once in a while, when you create new features, you inadvertently create bugs as well. So sometimes, we would get bug reports. This happens. It was a pretty good code base. We actually did a lot of things, or they had already done a lot of things right. So we didn't have that many bugs, but they came up from time to time. And then I found out that if the bug was precise enough that we could identify when things went wrong and sort of how which part of the system went wrong, we could usually find just from the bug report we could find the logs, the log entries that related to that particular behavior. And from that, it turned out that we could always get an understanding of what went wrong and reproduce the problem based on the logs, the understanding that we gained from the logs. And that turned out to be repeatedly an experience that we had. So I thought that was interesting, and I couldn't really. It was very pleasant to work with, because it took a lot of stress away from understanding defects in the system. You sort of you go and look at the logs, and you look through the logs a little bit and say, okay, now I pretty much understand it. I can reproduce that as a unit test or things like that. So when I went on my own way, after the engagement ended, I couldn't really stop thinking about what was it that made that logging, such a useful thing, because they didn't log a lot of stuff. Actually, they just logged they logged the stuff that we needed in order to reproduce problems. So I thought that was interesting. Did they know something that I didn't know, or did it just turn out that they were lucky? And these people were really skilled, but to be honest, in this particular instance, I actually think it turned out that they were lucky. There were circumstances around how that code base worked and the entire environment that it was running in, where it was quite obvious that there were things you wanted to log, and they went ahead and did that. But I still couldn't really shake the idea of what's the right amount of logging. So based on that experience with having this very nice, stress-free interaction with just enough logging, I thought you can actually apply a method to that. So this is what this talk about. It's about what to log, and also a little bit about how to log. I'm actually going to spend most of the time on what to log. So usually when I visit other organizations, so not the one that I talked about right now, but other organizations, code often looks like this. So you have a lot of code that is sprinkled with liberal use of log.debug and log.warning and log.info and whatever else you might have. And there's so much stuff going on there that it's noise that actually makes it hard to understand what the code is actually doing. And we should probably just spend a little time, discussing what it is that we're looking at here. So this is, one of my patented online restaurant reservation system demos. It's not patented really, but I've been using this this kind of demo application for a long time. It's one of those things where you scroll, you find a website or you use an app and then you fill in some details about the reservations you'd like to do. And then you can press the submit button. And this slide shows you how long I've been using this particular demo scenario. So I like to reuse my slides. So I copied that in. So I've been doing this for many years now. But the point is, this type of system, what we're looking at here is you press the submit button, it creates a JSON document, it posts the JSON document to an HTTP service somewhere. And the code that we're going to look at is the HTTP side of things, so not the client code that actually does that, but the code that receives that JSON document. That's what we're looking at here at the moment. There's this post method. It takes a DTO. That's basically just the data from the JSON document, and then it does stuff with it. But you almost can't tell what it is that it's doing because there's all of that logging stuff going on. So I don't think code should look like this. I'd like code to look like this. So this is more easy to read because there isn't all of that noise. Write code like that. But then you might say, well, yeah, but Mark, you just remove all the logging. So we need logs. You can't just remove all the logging and say, just because it's more readable, you can say, let's throw away all the logging. That's not what I did, actually. This code, it turns out, actually logs. We'll get back to how that works later on. Before we do that, I think we should just talk a little bit about, why do we actually log? Because there's more than one reason. As developers, we'd often think of ourselves first. So we think, okay, so we can do various things where we log debug information or other things that enable us to troubleshoot things, when things go wrong in production, and that's logging for our own purposes, which is fine. But there are other reasons as well. So maybe other departments would like you to log other types of things. So maybe the business, for example, would like you to log things that are important to them, what we typically call key performance indicators. So stuff like how many sales are you having, or how many page views, or whatever else you think might be interesting. And if you're operating in a domain where you are covered by law or regulations, you might also be required to leave behind an audit trail, which is also a sort of logging. So there's at least these three wide reasons why you'd like to log. There might be others as well, but I actually can't think of them. But that sort of thing, I think, captures most of it. But what they have in common is that you have a running system, and that running system produces some output that you can sort of peruse at your own leisure at a later time. It's typically to some sort of out-of-process system. So if we define logging that broadly, that's all logging, and that's pretty much. It turns out that it doesn't really matter that much, which of those use cases you have. So it's probably clear that we don't want to log too much, because if you've ever tried one of those turnkey solutions where you basically can click a little button or download some sort of framework, and then it will instrument all your code, and then you can try to run that in production. You probably know that it generates tons of data very, very quickly. If you log everything, that's not really practical, because it's going to generate so much data that you probably can't fit it on your storage devices, or if you're running in the cloud, you don't want to pay the price for that. And also just the act of logging everything that's going on in the system is probably going to slow down the system. So there's a limit to how much you want to log. On the other hand, you also don't want to log too little for obvious reasons, because if there's too little information in your logs, you can't use it for troubleshooting. Maybe you're not compliant with the regulations, or the business doesn't feel that it has good enough insights into what's going on. So there's also logging too little. So obviously what we want to do, we want to log just the right amount of data. So this is almost like this fairy tale with a girl who comes into a house that is empty at the moment, and she's trying out all the food that's left, and she's trying the beds and so on, and some of it's just a little bit too much, and some of it is a little bit little, but the middle thing is just right. Okay, so that's what we're aiming for. So obviously for that reason, that kind of logging, we're going to call that Goldilocks, or Goldilogging. Okay, So what does that actually mean? So we sort of need to figure out, okay, so what is Goldilogging? So what to log? So the key lies in repeatability. So this is sort of like a theme that we've seen in software development for the last few decades, is that repeatable builds are interesting. That's something that we actually want to strive for. Repeatable deployments is the thing that we might want to strive for. So what we are going to do here is we're going to look at something called repeatable execution, and that's a term that I just made up. But the idea is that we should be able to repeat that the execution that happened in production, based on what's in the log, and we can sort of replay that afterwards. And there's a method to the madness, and we can start at looking at code like this. So here we have two integers that are being added together. X and y are two integers, and we produce z, which is another integer from that. So first of all, would you log something like this? And it seems a little bit odd to say adding x and y. But on the other hand, you may not know what x and y are, because if this is something that arrives from outside of your system, it could be the user who's entering, in a user interface, they're entering two numbers, and then you're adding them together. I don't think it makes much sense to log that you're adding them together, but if they're arriving from outside of your system, it makes sense to log what the values are. So you could sort of think of that as sort of like a variation on that. At least log what x and y are. That might make sense if they're external values. But at least we could say something else. Would you log what the result is? It doesn't make sense if you know what x and y is. This is entirely redundant, because if you know those two numbers, you can always just recalculate. You can run the calculation again in order to get z. You don't need to actually log what z was, because it is repeatable. All right, so this is a function. This is a very simple mathematical function, x plus y. And in general, mathematical functions have this quality that you can always just repeat them, and they always produce the same output. That turns out to be a really interesting quality of functions in general. And it's one of the many reasons why functional programming is such an interesting thing, because we are working with functions, and we really like these things called pure functions for a lot of reasons. So we can learn from functional programming in terms of what do we have to log and what don't we have to log. So in functional programming, we really like these things called pure functions. A pure function is a function that has some extra qualities associated with it. So one of them is determinism. The same input will always produce the same output. That's what we just saw by adding numbers together. Or in general, that works for mathematics, but it also works for a lot of other things. So if you want to reverse the string foo, that is always oof. And such and going on like that. So you can actually write a lot of complicated, complex behavior as pure functions by just being deterministic. That's one side of the coin. Another thing you need to do is you need to make sure that there are no side effects. So side effect is something that changes the observable state of the system. So sending an email, or deleting a file on disk, or creating a row in a database, even repainting the screen is actually a side effect, something that a pure function can't do. So it's worthwhile being aware of pure functions have a lot of nice qualities. When they have these two qualities, there's a lot of other niceties that sort of follow from that. It makes the functions much easier to unit test, and also you can repeat the execution. So there's a lot of nice things about that. But on the other hand, we need to understand that since we can't do side effects, we can't really do anything that changes the state of the world. And in a philosophical sense, all software exists in order to change the state of the world. At least it exists to make money for some person, and that's also changing the state of the world. So we can't really do anything useful if we can't do side effects. And also, having something that is non-deterministic, like generating a random number, or reading contents of a disk, or getting the current time. That's non-deterministic behavior. We can't do that with pure functions as well. So it seems quite limiting. And it turns out it's not actually that limiting, but there will be a residual of things where we need state changes, and we need non-deterministic code, and we call those things impure actions. So it's not that in functional programming that we can't do impure things, it's just that we want to favor pure functions because they're easy to unit test, they're easy to reason about. It turns out we don't need to log what happens inside of a pure function, because we can always just run it again. Whereas the impure actions, they are non-deterministic, they may have side effects, so they are more difficult to work with. So we'd like to minimize the use of those things. So that's sort of like the general idea. So if we're looking at a little bit of a piece of C# code like this one, for example, so I'm not assuming that you're a C# developer, but if you're familiar with that sort of C-based language, you can probably follow along here. You might ask yourself, if we're trying to validate whether the DTO is valid or not, is that a pure function or not? And you can't really tell at this level of abstraction because C# or Java or TypeScript or basically any mainstream language, even F# doesn't allow you to actually make that sort of decision. So in order to answer that question, you have to go and look at the source code in order to actually look at it and say, does it do any sort of non-deterministic behavior? So this is a very simple example, just to get the point across. So the protocol here is that if we return the empty string, that's sort of like an error message, and an empty error message indicates that there's no error. On the other hand, if we return a string that's not empty, that indicates an error. That means the DTO is not valid. So we might ask ourselves, are there any side effects here? And it doesn't look like it's sending email or changing things on disk or anything else. So there's no side effects. Is it deterministic? Well, it's not relying on on any sort of random number generator, or it's not reading from disk or anything like that. So yeah, it's actually deterministic. So by looking through the source code, we can determine that yes, this is actually a pure function. But we have a problem, and that is, if we might have a stakeholder that comes by later on and tells us, well, your validation code is fine, as it's not wrong, but it's not capturing all the things that that we might want to reject. So, for example, if people are posting, trying to create a reservation in the past. That doesn't really make any sense. We can't accept a reservation in the past, so we should consider that to be invalid as well. And you go and say, okay, so I can deal with that. I'm going to change the code a little bit, and I'm going to say if the date is less than datetime.now, I'm also going to consider that an invalid date. Now, this turns out to be non-deterministic because if you have code like this where you say the input is completely known beforehand, and then you run the code. Now, if we're trying to make a reservation on the 20th of January 2020. As you can tell, the slides are a bit old now. Something happened in 2020 that sort of made me not being able to actually run this presentation back then. But if you're running this code on the 19th, you'll get just an empty message, meaning all is valid. And then if you run it 2 days later, you're going to get an error message saying this is an invalid date. So the same input, but now the output is different. So that's considered non-deterministic. So that's a bit of a problem. Determining whether things are pure or impure is actually not that easy. Well, you can go and read the source code, and in a very simple example, the one that I just showed you here, it's sort of fairly obvious. But if you have a lot of code and your code calls some other code that calls some other code and so on, the thing about purity or impurity is that it's transitive. So if you have something that calls impure code, the caller is also impure, and the caller of that is impure, and so on. So it's difficult to actually identify that. So it'd be really nice if there was a tool instead of using our own brains for that. And I have good news and I have bad news here, because the good news is such a tool does exist. The bad news is that it doesn't exist for any of the mainstream languages that you know. So C#, Java, TypeScript, Python, JavaScript, even F#, Clojure, whatever. Such a tool doesn't exist because the tool is a language. And there's more than one language, but sort of the biggest language that does this thing, that actually can make that distinction, is a language called Haskell. And I'm not assuming that you know anything about Haskell at all, so I'm going to give you a very quick crash course in how that actually works. So Haskell uses its type system to make the distinction between things that are pure and things that are impure. And with that type system, you can actually, if you've defined a function to be pure, and then you're trying to call an impure action from your pure function, the code's not going to compile. So that's basically how it works. So you're using the type system in order to determine whether things are pure or not. So a crash course in just reading type or function signatures in Haskell goes like this. So on the left-hand side, you have the name of a function. So I am pure is the name of a function. The 2 colons is basically just a delimiter from between the name and then the type of the function. You can think of that as a method signature like in C#. But and you read those from left to right. So the input is on the left-hand side, and you might have more than one input, but here we just have one. And then to the rightmost side, you have the output. And these are types, so we actually, in this case, we have a type called input, and we have another type called output, just to make things a little bit more explicit, a little bit explicit. So this is a pure function, and it's probably easier to see how that is a pure function if I show you what an impure action looks like. So you can see the impure action looks almost like the pure function, except that it has this little modifier called IO. So if you have this modifier that's at this IO modifier, it means that's an impure action. So by order of elimination, if that IO modifier is not there, then by default things are pure in Haskell. So you have to explicitly say that things are impure, otherwise they're just pure by default. So that's basically how you can distinguish, between impure actions and pure functions at the type level, which is pretty nice. You might then ask yourself, okay, so if you were doing this in Haskell, if you wanted to validate whether or not a reservation is in the future, if you did that in Haskell, how would you go about solving that problem? And here's just one way of doing it. And again, I don't expect you to actually be able to read the Haskell code. It's not really important. Just focus on the two top lines, which is the function declaration. So we have this thing called validate reservation. That's a function. And then I ran out of space, so I had to move the type declaration to a new line. That's possible. You can do that. So you can see here we have more than one input, but the output is something called either string reservation DTO. And don't worry if you don't understand what that means. The point that I'm trying to get across here is we look for the IO modifier and we don't find it, and that means this is a pure function. This is basically how that works. So how do we solve the problem of looking at the current time and seeing whether the reservation is in the past or in the future? Now, it's a really dumb primitive solution to that. We just pass in the value that represents what time it is right now as an argument to the function, and then the function just deals with that value. So translated to C#, it might look like this. We have a now argument, and then we're just checking on that, and that's a pure function. It's a very common thing to do in functional programming. And you might say, okay, so that's cheating, or some people might say that breaks encapsulation, and I argue that it doesn't, but that leads into a discussion of what encapsulation means. Or you might just say, but Mark, aren't you concerned that people may call this function with a value that's not datetime now? They may call this function with the value that is in 2030, or a value that is in 1980, or something else. And basically you can say, well, I'm not concerned for a couple of reasons. First of all, there's no side effects here, so it doesn't matter what they do. And also, I'm not concerned because I think that's actually an advantage, because that means instead of just running on the system clock, you can now perform simulations. So you can write unit tests that will test what's going to happen if I run this code in 2030, or what would happen in other sorts of circumstances. Or you can use your data from your logging system to say what actually happened yesterday when this code ran. You can pass those values in, and that enables you to perform simulations, and that's repeatable execution. It's basically just it's one of those many benefits that just fall out of pure functions, because you can always do that with pure functions. So that's considered an advantage. So it's not cheating. It's actually a very good thing to do it this way. All right. So I'm not trying to suggest that you should now go and throw away all your mainstream code bases and rewrite everything in Haskell. Now, if you want to do that, please hire me to help you. I would love to do that, but that's not really it's not my agenda here. What I find Haskell really interesting for is as a thinking tool. So I use Haskell for proofs of concept. So for example, if I want to learn, I have this online restaurant reservation system, and I'd like to write as much of it as pure functions, and just only the things that cannot be pure functions, I'll need to sort of isolate those and treat them differently. But I'd like to know in a system like that, what's impure, what's essentially impure, what can I not get away from being impure, and how much stuff can I actually do as pure functions. So writing a prototype in Haskell will enable me to sort of answer that sort of question. So that's what I did. And again, I'm not expecting you to know any Haskell, so I'm just going to briefly walk you through some of the type signatures here. So in the code base that we're looking at the moment here, this is basically my domain model. So this is where I model, what a reservation looks like, what a valid reservation looks like. This is how I make decisions about, whether or not I can accept the reservation or not. So here we have a little bit more of a sophisticated version of a validation function. And again, if we're looking for this IO modifier, you will notice that nothing here, even if we've, I've split this in multiple lines, there's nothing that says IO here. So this is a pure function. And we can sort of scroll down this, this file here and look at just the function signatures, and nowhere will you find the IO modifier. And that means this entire domain model here is actually written as pure functions. And we'll get back to this try accept function later on. This is sort of like the core decision logic that makes use of a lot of those other functions, in this file. So when I post a JSON document, it ends up calling this try accept method that then makes the decision: can we or can we not accept that particular reservation? And again, you'll notice, the output type here looks really horrible. If you don't know what that means, that's really not something that I'm going to try to explain to you in 2 minutes, because I can't. The point is, there's no IO modifier here, so it's a pure function. So that's nice. It's nice to know that you can write a lot of actually all the business decision logic as pure functions. Now, on the other hand, it turns out that interacting with something like SQL Server, this is actually saving things in SQL Server. That is not something that is possible to do as pure functions. These need to be impure actions. Basically, anything that performs I/O is impure, hence the name of that modifier, IO. So you can see it's sitting here. This is an action that inserts a row into the database. We have other things down here. Read reservation, this reads a single reservation, or it tries to read a single reservation. It says IO right here. Read reservations is a query that gives us a collection of reservations back based on a predicate. Our criterion, and it says IO here. So we have a clear distinction between things that are, impure and things that are pure, and it's nice to know which bucket things need to fall in. So there's that point. Now, I did oversimplify things a little bit when I said that this is the way you distinguish between pure and impure. There's actually a generalization of that impurity here, where sometimes you'll see things look like this, where it says monad IOM, and then there's an M, that M refers back to the monad IO. And if you see that M modifier, and the M modifier refers back to something called monad IO, that is also impure. This is sort of like a generalization of that IO modifier there. And don't worry if you don't understand it, it's just that, that's the sort of stuff that we go looking for. So we can see down here at the bottom, I have this little, this is sort of like an interpreter, and we can get back to that in a little while. But this is basically, it takes a little domain-specific language and runs an interpreter over the database. And you can see this sort of example here, monad IOM, and then the M appears over here. So that's an impure function, impure action as well. So the way that you basically, you have these pure functions, and the pure functions can't call into the database, but then you still need to do the database stuff, which is impure. So how do you sort of compose those two things together? And you do that at the entry point, basically. So it also turns out that doing anything involving the system clock is also impure because it's non-deterministic. So you can again see this monad IOM here, and so on. So what I've done here is that I've created some code that can enable me to sort of interleave pure code with impure actions via a set of interpreters that are all running and being impure. And then what I can do is I have this thing called log clock, which is also impure, but it's sort of like a wrapper around actually accessing the system clock. And what this wrapper does, it just logs, whenever I'm doing something that is an impure action, it's writing that information to a log. And the same thing goes with this thing called log reservation. It's just wrapping around the actual access to SQL Server, but it's logging all the information. So it's sort of like the decorator design pattern. Right. Okay. So let's have a look at that as well. So this system is actually an entire system. It's just a very thin slice, so it's sort of like a proof of concept. But it actually it does work. It can do HTTP traffic. It can save in SQL Server of all things. getting Haskell to talk to SQL Server was kind of interesting. I had to send a few pull requests. I sent some pull requests in 2019, and they were just merged last week, basically. So I think the original maintainer of that system had other things to do. So what I'm going to do here is I'm going to start the web server. I'm going to need a connection string to my database. I'm just running the database on my local DB here, so I can't remember the syntax of that. So I'm just going to I've kept that in a file. I'm just going to put that contents in my clipboard, and then I'm going to run the application. So let's see. So it's not that there's anything secret. The contents are right here. I'm using integrated authentication, so there's no passwords here. So now the server's running. It's running on port 8080. So now I need to figure out a way to post a JSON document to port 8080 on my local machine. So I'm going to use another terminal for that. So I can use curl. That's my preferred thing. Do yourself a favor if you're doing any sort of HTTP work. Use curl. It just makes things easier because curl is always around. Someone told me yesterday that curl is actually running on the Mars rovers on Mars. I'm sort of working. It's getting my head around. Okay, so what's the ping time of TCP/IP from Mars to the Earth? It's like 28 minutes, or something like that. So how does that work? I'm not sure that I understand that. Okay, so what I want to do is I want to post to a resource called reservations. I'm going to need to give it a content type. I'm going to need to tell it it's application/JSON, because otherwise there's a little bit of content negotiation going on there. And then I want to write my JSON document. So the way it's designed, I need to give it an ID. The ID needs to be a GUID. So let's see if I can do this and then like this. So I need to create a new GUID. So I can use this thing called UUIDgen. UUIDgen. So that's just going to create, every time I run this code, it's just going to create a new GUID if I've done things correctly. I'm going to need a date. So I'm just going to use the date of tomorrow, so 2022, 06/03, and at 1900. And I'm going to need a name for the person, name for the reservation. So we're going to say Burrows is going to make the reservation. We need an email address for Il. So that's going to be ilbose@example.com. Like that, and we need a quantity. That's the last thing, and we'll try to make a reservation for 2 people. Does that look okay to you? Did I forget any quotes or things? No. Okay, let's try it out. It's always a little bit stressful here. Okay, so it says 200. Okay, so it looks like it's worked. So just as a sanity check, we can go. I actually have access to the database sitting here in SQL Server. So if I go and refresh that, we should now see a row in the database. So if this demo had been running, if I'd been doing this in 2002, you'd be very impressed. But you can have an HTTP thing that actually ends up in a database. But that's really not the point of the demo. The point of the demo is that while this happened, the system logged all the impure actions. So where do you always put your log files? On the desktop, obviously. This is just proof of concept code, right? So in this case, it's looking like this. So this is basically just something that, this is a format I choose to use because that's machine readable to Haskell code. It's basically just sort of like serialized Haskell code. But what we can see here from the entries is that, the first thing that happened is that, part of the system, asked for the current time. There's no input to that question because you're just asking what is the current time, but then the output was this particular value. Then the system asked, made a query against the database, read the existing reservations, using this particular date as input. It got, the empty collection as output because there's no prior reservations in the database. Then it, called this method called create reservation, and it also logged what the input was. And if we scroll to the end, we can see the output is nothing. This is called unit, but it basically means void as output. And then I also logged the entire HTTP request and response. So that's why you're seeing a lot of escaped strings here, because it's sort of the strings that I escape within strings and so on. So that's a little bit confusing. But that's basically what happened. So what I can do is that I can start, let's see, on my Haskell prompt here. I'm going to stop the web server, and I'm going to start something called GHCI. So GHCI is a REPL, read, eval, print loop, where I can just ad hoc interact with values in Haskell. And again, don't worry too much about the syntax. It's more like what can you do with the values here. So there's a little bit of color going on here, and it's quite busy to look at. So I'm just going to simplify the prompt a little bit here. So I'm just going to say it's going to look like this. And I'm going to clear the screen here. So I'm going to do something like that. All right. So the first thing I want to do is I want to load that file. So again, don't worry too much about the syntax. There's a built-in function or built-in action called read file, and I just need to find my file on the desktop. So it's something like users mark desktop log.txt. All right, so that reads the file. So if we don't see any exceptions, that just worked. If you're wondering what L is, L is just the log. It's just the contents of that file, and it looks quite unreadable here. So we want to parse it. We want to interpret it into something that are actually proper Haskell values. So the way that I can do that, I'm going to create a new value called replay data. And the way that I'm going to do that is I think I have a function or an action already. This is a function that's called replay. Let's see, replay, something like replay data from a log. Okay, so if we look at what that looks like, replay data, that looks a little bit more, it's a little bit more readable. Still quite, abstract. But we have all the information, and now they're actually Haskell values. It's like, if you've done this in C#, now you actually have C# objects. This is a collection of objects, basically. So, for example, if we're interested in, if we want to see what was the reservation that was actually logged, I'm going to need that later on, so I'm going to call that R. So I can get the head of, that's just the first element in a collection of something called observations of post-reservation, from that replay data. So there's my reservation. So let's clear out this as well. It gets a little bit busy. So let's start here again. So let's just, this is the reservation that is in the log. We've now passed it, and I have access to it. So if I'm wondering what happened, I'm not really, but just, if in case I am, I talked about this function called try accept before. So I can try to ask, what's the type of that? So when I go :type, I'm not trying to run the function. I'm just, basically looking at the type of it and saying, what's the type of it? And that looks really complicated. But basically what it turns out is that it needs a reservation as one of its input arguments, and then it needs something else. And those something else is the seating duration. So this restaurant has a seating duration where you have a table for a couple of hours, and then you have to leave the table because there might be other people. And then we also have a table configuration. And I can read that from a config system that I have already. So I do that. So seating duration is something called a nominal diff time. That is basically the same thing as a time span in C#. So that's just the duration. This is 9,000 seconds. That's 2.5 hours. Tables, it's the table configuration from the restaurant. So this restaurant has 4 tables. It has a table for 2, it has a table for 4, for 6, and for 8. So I thought that was easy to remember because that becomes important a little bit later on. So now I have those values. So what would happen if I try to call, I can sort of ask the type system, if I try to call try accept with the seating duration and with the tables and with the reservation, then I lost the, and then it came back. Okay, so what it would give me is this horrible looking thing here, except T of blah, 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 blah. And you don't need to understand exactly what that is, except that it is a pure value. It is not something that is impure. But the pure value actually describes a little program in a little DSL, and you need an interpreter to run over that program in order to figure out, what's actually going to happen. This is how you interleave pure functions with impure actions. And what happened when I ran the actual code was that interpreter then went and interacted with the database. But what I can do now is I can define another interpreter that instead of interacting with the database is going to replay what happened in the logs. So I have another function here called replay. I think it's called replay, yes. And it takes the replay data that we already have, and it takes one of those exceptee horrible-looking things, and then it produces a pure value and something called an either value that indicates whether it's a success or a failure. That's basically how that works. So you notice all of these are pure functions. There's nothing that says IO here, so the replay would be a pure function. So what we can do is I can find the try except here, and I can say, let's replay that. With the replay data that I have, and I just need to put a little symbol there, and it produces the value right of nothing. So that basically just repeated the execution that happened on the server based on the log data. And if it seems a little underwhelming that it just the output is right of nothing, it's because this was trying to save something in a database, and that's all about the side effect. And the side effect doesn't really produce any output, or it can, but we didn't do that in this case. So there's no output. It just means things went well. There was no output. Fine. Okay. So the point of this is, again, it's not that I'm not trying to convince you that you should write all your production code in Haskell, but it's interesting to do those kinds of proofs of concepts because we learn something about what is pure, what can be pure, and what has to be impure. And what we've learned here from this little proof of concept is that the impure actions in a system like this one is, first of all, the database, and the system clock. Now, this is not surprising. If you've done this sort of exercise a couple of times, you will know that databases are always impure because they involve I/O, and the system clock is always impure because it's non-deterministic. But there might be other sources of impurity as well. But in this state of the application, that's basically what we have to deal with. So in order to have, in order to figure out what to log, basically what we've learned so far is that we don't need to log what happens inside of a pure function because we can always just rerun the function. But the things that we can't just rerun is all the stuff that's impure because that is non-deterministic or may have side effects. So that's the stuff we need to log. No more than that, but also no less than that. We need all the impure things logged, but that's also going to be enough. And that's sort of like what that little replay demo also demonstrated. So what we can now turn our attention to is once we know that, we can think about, how do we then do that in a sane manner? And not like this. All of those log statements that are sprinkled all over the code, that just makes the code really unreadable. So that's not what we want to do. So I also wrote the code in Visual Studio in C#, so we can now try to have a look at that. And the post method that I think is more readable is this one here. So it doesn't look like it's logging, but it is. And the way that it works is, you'll notice, for example, that it's not accessing datetime.now. It's doing something called clock.getCurrentDateTime. And if you know the .NET API, you think, what's that? I've never seen that before, because normally you do datetime.now. So if you go to the definition here, you'll find that this is actually a method on an interface called iClock. And I define this interface because I know the system time, the clock is non-deterministic, so I need to hide that behind an interface. So that's one thing. Also, it turns out that the database interaction, so for example, if I'm reading the reservations here, if we go and have a look at that, that's another interface. This is a repository interface that defines read reservations, and it also defines a method called create. So you probably, most people will probably have some data access that's hidden behind an interface already. So that should be sort of, not surprising. And if we want to see, what kind of classes implement that interface, first of all, we'll find something that is not surprising at all. We have a class here called SQL Reservations Repository. And if we just try to scroll a little bit, we'll see we have some SQL code actually sitting here. This could also be based on an ORM. It doesn't really matter, but it's just like this is the thing that actually talks to SQL Server. So that's not surprising at all. Now, it turns out, though, that if you at other things that implement that interface, there's another one. There's one called Log Reservations Repository. And this one also implements the interface, but it does that by taking an inner one and wrapping around that. So this is a design pattern known as the decorator design pattern. And if you're wondering, okay, so what's the inner one? We can go and look at the place where we actually create this thing, and you'll notice, not surprising, that the inner one for log reservations repository is actually that SQL thing here. But it might be something else, but that's the way that I usually configure those things. So inside of the log is sitting the SQL implementation. So what happens here with the create method, for example, is that I take the reservation, then I log that this interaction takes place, and then I call inner.create. And this is a void method, so it doesn't return anything. The same thing goes with the read reservations thing here. I'm calling inner.read reservations first, and then I have the output of that. I log that this interaction took place. What was the input, what was the output, and then I return the reservations. And I do the same thing with the system clock. We can very briefly look at that if we're interested. There's a system clock implementation that just delegates to datetime.now, but then it's decorated by this log clock that, not surprisingly, just logs that we accessed the current time and what the time was at that point. All right, so I have the system running already, so I should be able to go and interact with it and see if that actually works. So it's running on a different port, and I just need to figure out what that port is. So it's sitting right here. And if you're wondering why it looks like there's an error at the moment, it's just because this is a proof of concept. It's a very thin slice through the entire system. So this system actually doesn't support HTTP GET requests. It only supports a post. And that's why we see that this 404 error here, this is entirely expected. I just needed the port number. So I can try to basically reuse that request from before, just with a different port number. Maybe just to keep things a little bit more interesting, we should change the name here. So instead of having L making the reservation, it'll be her brother Rain, and so we'll have rainbows here instead of elbows. So if you remember the table configuration of this restaurant, it has table for 2, table for 4, for 6, and for 8. So now we're trying to make another reservation on the same date, on the same time, for 2 people. Now that should still be possible because we have a table for 4, maybe not good business for the restaurant, but if they don't have any other reservations, that could work. Now, what I did here is that I actually I introduced deliberately a little bug in the system. So if I try to actually run this, it doesn't work. Oh no! You'll notice here it says internal 500 internal server error, couldn't accept. What went wrong? There's a bug in the system. How can we troubleshoot that? If only there were logging. Let's see, where do we put the log? We can just put the log in the file there. You can see there's this thing called log.txt here. So yeah, we actually logged what happened. That was fortunate. Let's just clear this and have a look at it. So what's inside log.txt? Well, in the C# demo here, I decided to do that as a JSON document instead of this Haskell code instead, because that's easier in C#. But the idea is the same. We have all the data that we need in order to figure out what actually went wrong. So what I can do with this is I'm going to move that log file to my unit testing library. So booking API.unit tests, and I'm going to call it repro1.txt. So I'm just moving the file there. And then if I go and have a look at my code in Visual Studio, if I scroll down and have a look at my unit tests, you can see repro.txt is sitting right here. And one thing I actually want to do straight away is I'm just going to make that an embedded resource. And it's basically because I actually want to read the contents of that file. And when doing that from a unit test, I think it's easier to just make it an embedded resource and read it from there, because otherwise you need to manage actually moving files and copying files around, making sure that they're cleaned up afterwards and so on. Your mileage may vary, but that's what I usually do. So I'm going to add a new test class here and want to be able to reproduce this problem here. So I'm going to add a class called repros. And make it a public class. I'm using xunit.net, so I have to decorate it with this fact attribute here. And let's say public void, I'm just going to call this repro1 as well. So this is the first repro that I want to do. So the first thing I want to do is just load the log from that embedded resource. So and I did cheat a little bit, so I have an API for that. So I'm just going to say, okay, I'm going to load repro1.txt from that embedded resource there. So L, let's call it log. That's a little bit easier. So L is just a string, and you recall that that string is actually a JSON document. Now, the next thing I want to do then is I want to have a system under test. I want to, be able to create, an object and test this. And I also need to read the data transfer object, the DTO, from the log. So what I can do here is I'll show you how this works afterwards. But I have a little API for that as well, where I say load the reservations controller post scenario. And then what it does, it returns back the system under test. That's my reservations controller, the one that has the post method. And then it also gives me a DTO that was passed out of that log file. So that's a reservations DTO object. And I can now exercise my system under test. So I can say post that DTO. So again, I'll remind you the DTO is passed from the log file. And then, what's actually supposed to happen, this actual here is something called an action result. So I want to say that this should be assignable from something called an OK result, because I would expect this to work. I also know that it didn't. I'm going to need to import a namespace here. I also know that it didn't. So if I try to run my tests now, I would expect this one to fail, because that was a bug in the system, and it does. It actually does fail. So it says, I expected an OK result, but I actually got an object result. And if you try to sort of examine that object result, you'll figure out, or you'll find that it actually contains a 500 internal server error with the message couldn't accept. So that's how that works. So we now have a nice repro of things here. And I can show you in a little while exactly how that works. But the nice thing about having a repro is that now you can actually start troubleshooting. So I deliberately made this little piece of sabotage here. So I know where to go and look for it. So the defect is actually sitting around here. So I'm just going to add a breakpoint just to prove a point here. So I can add a breakpoint. I can go back to repros. I can decide to go and debug that particular test, and I'm going to wait a while because that takes some time. Let's see. I think we hit the breakpoint now. So what's happening when we're running this test is that it's using the log information to replay what actually happened, and then at this point we are going through a loop and trying to find the index of a table that can fit the reservation that we're interested in, and we find the index. It's the first table in the collection in that array. So the index is 0. So we actually did find it, but then, so we say, okay, so we found the table. That means we can remove the table, down here. We can remove the table of that index. Oh no, it returns false. And we have an off by 1 error here. So it shouldn't have been, less than or equal. It should just have been less than. So now we understand what the problem is. And I knew that because I actually deliberately introduced this bug. But the point is, you can actually use the debugger, or you can use all your other troubleshooting skills, because now you have a deterministic repro of the problem. And then once you find the problem, you also have a nice repro test that you can then run and see that you now fixed that that particular defect. So how does this work? Let's go back and have a look at the repro. So what happens inside of this method here is that it takes the JSON document and it starts to parse that JSON document, and it looks at all the different operations that it encounters and sorts them out into various different collections, and then it creates some replay implementations of those interfaces. So it's probably easiest to understand the replay log. the replay clock, sorry. So when you initialize the replay clock, you take all the observations that you've seen in the log file of, whenever the system is asking for the current time, you put that in a collection. This is an IEnumerable of date time. You pass that to the constructor of the replay clock. It creates a queue out of those because they should be in order. And then every time we call get current time, that's the interface method. We dequeue one of those values that comes from the log file, and we return that. So that's how it's replaying what happened. And the same thing basically is true for the repository. It looks a little bit more complicated, but basically the idea is the same. When we call read reservations, so read reservations might be called with more than one date time. So the first level of data that I have here is a dictionary where I index into the dictionary and say, okay, I want the entry in that dictionary that corresponds to this particular date. And I may have seen more than one observation of that particular date. So inside of that dictionary entry, there's a queue because there might be more than one observation of that query. And then again, I dequeue one of those values, which is an IEnumerable of reservation, and then I return that. So these two things, the repository here, which is a replay repository, and the clock, which is a replay clock, I now pass them as dependencies. I inject them into the reservations controller. So when the reservations controller and all sorts of other things that might want to interact with those things, when it calls methods on those classes, it replays what was in the log. So that's how that works. Right. Okay, so we're pretty much done. So just to summarize, we really favor pure functions because pure functions, we can always just repeat that execution to get the result. If we know what the input to the pure function is, then we also know what the output will be. We can just run the function again. So we want to have as much pure code as possible because all the stuff that happens in pure code, we don't need to log that. What we need to log is the impure actions. In this case, we saw one example was the system clock. We want to log all of those accesses. And also, we are accessing the database. We want to log that as well. So the way that I do that, I'm using this decorator pattern where I'm wrapping the actual implementations in another implementation of the same interface that then performs the logging, the decorator design pattern. So basically, in order to do this, you sort of need to move towards a functional paradigm because otherwise you're just going to have a lot of impure and pure code interleaved. But if you can do it, here's the recipe. So first of all, identify all the impure actions. So in this case, it was the system clock and the database. Model those actions as polymorphic types, an interface or base class, because otherwise you can't use the decorator design pattern. I just stick with interfaces. So make interfaces out of the database access, make interfaces out of the, accessing the system clock. If you have other things, if you need to send emails, you need to hide that behind an interface as well. If you want to generate random numbers, you need to hide that behind an interface. And once you've defined all of those things that are impure, behind an interface, use the decorator design pattern to, log from the decorator. And that means when you're using one of those polymorphic types, there's no logging noise in your actual code. It just happens automatically that, whenever you're doing something impure, it's being logged to a log destination somewhere, and then profit basically. Use the logs to enable replay. So it's just to make sure that I get my point across here. It's not that I actually recommend that you create one of those replay machineries that I just showed you here. The reason why I showed you this replay stuff is just to get the point across how deterministic it actually is if you have the right amount of information in your log. Now, I didn't do that when I worked for that company that I talked about 7 or 8 years ago. What we did was basically just look through the logs, and then there was always enough information in the log that we understood what, we could get an understanding of what the problem was, and then we could go and write a unit test that reproduced what happened at runtime. Maybe using some of the data that we could pull from the log. So it was more like an ad hoc process. Go and look at the logs. Maybe take some copies of the things. Write a repro. And then run that one. So it's not that I have this fancy machinery. This was just to get the point across. But that's basically what I have in mind for this talk. If you want to see more of the details of how that works, you can go to blog.plur.dk and find the archive, search for repeatable execution, and I have a little blog series with 3 blog posts that walks you through that and shows you some more of that code. So if you're interested in that, you can find it there, and it's all free. You can also go and buy some of my books if you'd like to. And in Code That Fits in Your Head, I talk a little bit about that, but actually most of the details are on the blog, so that's probably where you want to go. And I'm out of time. That fits perfectly because I'm also out of slides and out of content, so thanks for coming.